Hello.
Hello, good evening.
Yeah.
Good evening, sir.
Good evening.
Okay, I am Sachin, PhD student in the Indian Institute of Science, EC department, and I'll be conducting problem solving sessions for the course. So I'm not a regular TA in the sense that I can't give you information about exams and quizzes or any of the other stuff that you might be interested in. I'll only be solving assignments, previous year assignment questions. If you have any questions regarding the logistics of the course, then you'll have to ask in the discussion forum. So if you go to your course page, you'll find a Q&A section. There you can go to there'll be a Google group to ask questions. Uh, there you can ask. Okay, we'll start now. So these are previous year questions, so they'll be similar in format to your current assignment questions. Maybe the numbers will have changed. That there won't be too many differences. Just give me a minute. Okay, question one. Determine the Nyquist rate for the signal x of t is equal to 1 plus cosine 100 pi t plus sine 200 pi t in samples per second. So since first week is a introductory week, the questions are mostly from your digital communication course that you would have done in your undergraduate. They are not very hard. Anyway, in your assignments you'll have options, but I'll only give options if they are necessary. This is simple. X of t is 1 plus cos 100 pi t plus sine 200 pi t. So 1 has a frequency 0, it's cos 0 pi t. And you have a signal with frequency, uh, angular frequency omega, which is 100 pi, and another with angular frequency omega of 200 pi. So you have sum of three signals here. The first one has frequency 0 hertz, second one has frequency omega by 2 pi, which is 50, and the third signal has frequency 200 pi by 2 pi, which is 100 hertz. The Nyquist rate is simply double the maximum frequency. It's 2 times 100, 200 hertz. So if you sample at this frequency, you can easily reconstruct it. That's just a basic question from signals and systems. Question 2. The audio signals with one-sided bandwidth 12 kilohertz is sampled at Nyquist rate and quantized to 8 bits per sample. The data rate of the quantized stream will be this is similar to first question in the sense that you are sampling a signal, but in addition to that, you are also quantizing it. So they have given the signal has um, bandwidth of 12 kilohertz. So the sampling rate or the Nyquist rate, it's sampled at Nyquist rate, which is 2 times the frequency. It's 2 into a 24 kilohertz. and then you quantize it to 8 bits per sample. So the data rate is the number of bits per sample into number of samples per second. So here sampling rate is actually is measured in samples per second, but you usually don't write samples per second. We just write hertz sometimes. But actually, it's samples per second. Bits per sample is 8. Samples per second is 24 kilohertz. One 92 kilo. You shouldn't forget the units. It's not hertz. It's kilo, and the units are bits per second. kbps. Even if you don't really remember the exact concept, you can just look at the units and figure out the answer. Except that you should know that sampling rate is twice the Nyquist rate. So if you are unable to figure out the answers to these questions, if you feel that you don't know the answers to these questions, then you might want to reconsider taking this course, because this is a kind of prerequisite for the course. All these things won't be taught in this course. Third question, using a 8 PSK modulator turns dash bits into a symbol. Well, we know that 8 PSK has 8 constellation points, and each of them is a symbol. So how many bits can you accommodate? If you have 1 bit, that can correspond to 2 symbols. So if you group 2 bits together, you can have 4 symbols. If you have 3 bits together, you can have 8 symbols. Basically, with n bits, you can have 2 power n symbols. And since you are using 8 PSK, you need 8 symbols, which means you can use 3 bits. The answer is 3. K bits you can represent 2 power k symbols. Here 2 power k is 8, which is 2 power 3. Therefore, 3 bits per symbol, you could say. Question 4. A 16 QAM constellation is given below. The average symbol energy is it's your regular 16 palm, nothing special. This is 3 minus 3. Energy of a symbol is square of the distance from the origin of the corresponding constellation point. So here you can see these 4 points are at a distance. So it's a right angle triangle. This is one side is 1, the other side is 1. So the distance is square root of 1 plus 1, which is square root of 2. And the square of the distance is just 2. We got we have got 4 of such points. So there are 4 symbols with energy square root of 1 square plus 1 square whole square, which is 2. Then there are these points 1, 2, 3, 4, 5, 6, 7, 8. All of them are at the same distance from the origin, and their distance is this is 3, this is minus 3. So their distance is square root of 3 square. This is 3, this is 1. 3 square plus 1 square. And that squared is just 3 square plus 1 square, which is 9 plus 1, 10. So there are 8 symbols with energy root of 1 square plus 3 square whole squared, which is 10. And finally, there are 4 corner points. So there are 4 symbols with energy Corner points are at a distance 3 from the x and y axis. So from the origin, they're at a distance 18. Now, I've asked us the average symbol energy. So we take the average of all these energies. So, average symbol energy is the total energy for all symbols divided by the number of symbols. There are 16 symbols. Total energy is 4 symbols with energy 2, 8 symbols with energy 10, 4 with energy 18, the whole thing divided by 16. That's 160 divided by 16, which is 10. Next, question 5. Consider the magnitude response. And by magnitude response, they mean the magnitude of the Fourier transform of a signal x of t as shown in the figure below. X of t is a. First, I'll draw the figure, then I'll give you the options. So, this is the magnitude response of the real part, and this is the magnitude response of the imaginary part. So, from this, you have to tell whether it's a real baseband signal, B complex baseband signal, C real passband signal, or D complex passband signal. I'll leave you with that question. Think of the answer. I'll be back in a minute. All right. So think about the magnitude response of what this magnitude response could mean. So if you have just a pure cosine, if you had this cos of 2 pi f t, you could write that as e power j 2 pi f t plus e power minus j 2 pi f t divided by 2. Now, if you take the Fourier transform of this, that will be simply the sum of the Fourier transform. Now, I won't teach you how to do the Fourier transform. You should have learned it in signals and systems. But for a complex exponential, the Fourier transform is just an impulse. So, what exactly? The Fourier transform is a representation of a signal as a kind of a sum of uh, complex sinusoids. So, as a sum of complex exponentials. So, this signal is already a complex exponential. So, it it's just a single frequency, a complex exponential. So, in the frequency response, there will just be an impulse. Now, this will be, I'll take out the half common, this will be delta of 2 pi times delta of so to differentiate between this frequency and function variables. So this will be x of f. So it will be f 2 pi into f minus f naught plus 2 pi into delta of 2 pi times f plus f naught, something like that. Just pi times delta. 2 pi f is omega, so we'll just write it as omega minus omega naught plus delta of omega plus omega naught. So this does not have any imaginary part in it because there's no I or j, right? It's just a real signal. So the imaginary part of this is just empty. It's zero everywhere. It's x of f versus f. So if you take the real part of x of f versus f, you have one impulse at omega 0 and another impulse at minus omega 0. So this is the Fourier transform of a cosine signal. Similarly, if you do it for a sine, you'll get something like this. So you can see that this is even. If you flip it about the y-axis, it's the same. So it's an even signal. But for the sine, you'll get an odd signal. And for the sine, when you expand it out as a sum of complex exponentials, in the denominator, if you do this for sine, you'll get 2j. So there will only be imaginary part in the Fourier transform of a sinusoid, sine signal. So we'll get imaginary part of x of f. This is for sine to be like this. Now that is for sinusoidal signals which are at only a single frequency. But here you have a band of frequencies. But still the same kind of principle applies. So the parts related to the cosine aspect of the signal will give you an even, the real part will be even, and the parts of a signal that are related to the sine signal will have imaginary part to be uh, an odd signal. So since both cosine and sine are real signals, this is looking at the magnitude response of a real signal. Well, that was just an example. If I had to make it more concrete, if the magnitude spectrum of a signal is conjugate symmetric, it is a real signal. By conjugate symmetric, what we mean is the real part is even and the imaginary part is odd. In that case, if you flip the sign of the variable and also take the conjugate of the uh, function, then you will get back the function itself. So x of minus f conjugate will be x of f. Then it is a real signal. You can also see that it is not concentrated around baseband, it's a passband signal. So this is the magnitude response of a real passband signal, which is option C. I'll just tick it. Okay. Consider the communication system explained in lecture 1. Pulse shaping is used for AISI removal, improving bandwidth efficiency, frequency offset correction, and none of the above. So here, actually, pulse shaping is used to improve bandwidth efficiency, but it can also be used for ISI removal. So if you have to pick one option, at least in this course, uh, it's better to pick improving bandwidth efficiency. But if they ask you for multiple answers, you can pick, you have to choose ISI removal and improving bandwidth efficiency. So just say it improves bandwidth efficiency. Question 7 is a true or false type of question. Which of the following comments about statements 1 and 2 hold good? Let me change the question. Which of the following statements is true? Statement 1 says that fading causes fluctuation in signal strength and the rate of this fluctuation depends on the Doppler. And both statements are true. This happens in wireless communication when um, the receiver is there is a relative movement between the transmitter and receiver, which causes a Doppler shift in the frequency of the received signal, and that also depends can change depending on the path that this received signal is taking. So you can have multiple multi-path receptions, and in each path the Doppler can be different. So this can cause a difference in the this can cause fluctuations in the signal, which will affect uh, the rate of the fluctuation. That's just a conceptual question. Next, they are asking a base station is transmitting a signal with a power of 40 watts. The power level in dB watts and dB milliwatts are. Again, this is very straightforward. They are giving you the power in watts. To calculate the power in dB watts, you just have to take the logarithm of the power in watts to the base 10 and multiply it by 10. You have to multiply it by 10 because it's deci. If it's just bell watts, then it's log of the power in watts. If it's decibel, you have a multiplication factor of 10. And here it's 10 log 40 to base 10. You can use a calculator to find the log of 40 to base 10, and the result will be 16 dB watts. So that's a unit of measurement for power. And then when you want to measure power in dB milliwatts, it's actually measuring power relative to a reference point, and in this case, the reference point is 1 milliwatt. So the power in dB will be 10 log to the base 10 power in milliwatts. So how much larger is it compared to a milliwatt? That is expressed on a logarithmic scale. So here it's 40 watts, which is 40,000 milliwatts, and that will be 46 dBm. So log 40,000 is log 4 into 10 power 3. This is log 4 plus log 10 power 3. Log 10 power 3 is 3 since it's base 10. Log 4 we already found in the previous question, which is 1.6. So 1.6 plus 3, 46 into 4.6 into 10, which is 46 dBm. Question 9 is similar to an example shown in the lecture. We have a 4G cell phone with a front end receiver bandwidth of 20 megahertz operating at 27 degrees Celsius. The cell phone has a noise figure of 3 decibel. If the receiver sensitivity of the cell phone is minus 125 dB watts. What is the minimum SNR required to detect the signal? Quite similar to one of the examples that was done in class. So first they have given the temperature and bandwidth. So from that we can figure out that we have to take into consideration the thermal noise floor. So this is noise that is caused just due to the temperature, which causes electrons to move out randomly. And this thermal noise floor is given by 10 log to the base 10 of K into T into B. K is the Boltzmann constant, which is in joule per Kelvin. It's 1.38 into 10 power minus 23. T is the temperature in Kelvin, because we have taken K also in Kelvin. So 27 degree Celsius is how much? Yeah. 27 plus 273 is 300. And your bandwidth, which is given as 20 megahertz. You plug in the numbers in this formula, and that should give you TNF to be in dB watts minus 130.82. Now the receiver noise floor will be this TNF plus the noise figure, which is how much degradation the device itself, the cell phone itself causes, and it causes a degradation of 3 dB. So finally, the minimum SNR is the receiver sensitivity minus the receiver noise floor. Receiver 20 sensitivity was given to be minus 125. This is dB watts. Minus 125 minus 130.82 plus 3, that will be 2.82 dB. Okay. Next question is just a definition. So multipath delay spread is the option A, difference between the time of signal transmission and signal reception, which is not multipath delay spread. Option B says the difference between the time of arrival of the first and last copy of the transmitted signal at the receiver, which is the definition of multipath delay spread. So the signal goes through multiple paths with different delays. The time difference between the first copy that arrives at the receiver and the last copy that arrives at the receiver from after bouncing off different paths is the spread, delay spread. The spread in general also works the same way, not just in wireless communication. A delay spread or any other spread would be the max value minus the min value. I'll write out the other options also just for your reference. Shortest difference between time of arrival of two multipath components of the signal. It's not correct. It can't be any two components. It has to be the fastest and the slowest component. That's it. Uh, Another simple problem. Consider a 4G device using 64 QAM modulation and transmitting at a data rate of 6 Mbps. Yeah, yeah, yeah. You marked it with this light blue color. Then we are using 64 QAM and transmitting at 6 megabits per second. Assuming Nyquist pulse shaping is used, the duration of each QAM symbol is, so they've given it's 64 QAM. So per symbol there are log 64 base 2, which is 8 bits. And the data rate is 6 megabits per second. So the symbol rate is the data rate in bits per second divided by the bits per symbol. So in 1 second you are transmitting 6 into 10 power 6 bits, but each, sorry, it's not 8, 6 2 power 6 is 64, so it's 6. So every 6 bits is a symbol. So the number of symbols you're transmitting in each second is just 1 into 10 power 6. 6 bits per symbol. So your 1 mega symbol per second. Now, in each second, you are transmitting 10 power 6 symbols. So, to transmit one symbol, what is the time you take? So, the time duration of each symbol is simply the inverse of the symbol rate, which is 1 microsecond. Quite straightforward. But you just need to know what QAM is to find out how many symbols, how many bits there are per symbol. If you know that, rest of the things you can figure out by yourself. You don't need to memorize any of these formulas, but you should know what QAM is. Question 12. Consider the GSM frame format discussed in the lectures. If you remember, each frame was split into 8 time slots, and one user gets one of those 8 time slots. A user gets assigned one time slot per frame, and the gross data rate, the example that was given in the lectures, it turned out to be 22.8 kbps. The example is fully worked out. You can go and check in the lecture slides or the lecture video. Now here the change is they want us to calculate the gross data rate if six tail bits. So there are three tail bits in the front of the uh, data. There are three in the front and three in the um, three at the end. So if those six tail bits were instead used to transmit data, if they are converted to data bits, in addition to the existing 114 data bits. So there are two segments, each of 57 data bits, which gave us a total of 114 data bits. Now we are saying six of the tail bits will convert it to data bits. In this situation, what will be the gross data rate? So total data bits is 114 plus 6, which is 120. Gross data rate. So you can go and check in the lecture that the frame was of duration 576.92 microseconds. So you get to transmit 120 bits in 570, approximately 577 um, microseconds. That is, per frame you get to transmit 120 bits, and the duration of the frame is 577 microseconds. But you're only transmitting for 1/8 of the time because there are 8 time slots. And also there were two frames where you are not allowed to transmit your data. So out of 26 frames, you could only use 24 frames. Every 13th frame was could not be used to transmit data. So it is 24 out of 26. You can do the calculations yourself and you'll get something around 24 kbps. If you have options, you can just do a rough calculation. This is about 600, 10 power of 6. The options are all in kilobits here. And they didn't give you the options, but in your assignment you will have options. Do 24, you can write this approximately 25. So this will all cancel out. So it's approximately 24 kilobits per second. If options are not given, if it's a fill in the blank type of question, then you can just use your calculator. How we got this, you can check in the lecture videos. This is the last numerical question of this week. So, a cellular phone has a 2000 mAh battery. Assume that the phone draws 50 milliamperes in idle mode and 200 milliamperes during a call. Approximately how long would the battery last if the user makes a 4-minute call every hour? So the battery capacity is 2000 mAh, which means you can draw a current of 2000 milliamperes. If you draw that much amount of current, you can use it for 1 hour. Anyway, the amount of current that you draw into the amount of time that you use in hours should be 2000. You could draw 400 milliamperes for 5 hours or 100 milliamperes for 20 hours. So the capacity that they are given is in terms of the product of the current drawn into the time in hours. They were given that every hour you have a call for 4 minutes, and when you are making a call you use 200 milliamps. So you can say that the current used up, we'll calculate it for 1 hour first. In an hour is 200 milliamperes for the call, and the call is for 4 minutes, but we'll calculate it in terms of, we'll change the units to 1 hour by dividing it by 60, and the remaining time you are keeping it idle, during which you draw a current of 50 milliamps into 56 by 50, 60 hours. So this is per hour. So it's 60 milliamperes. And the charge available is 2000 milliamp hours. So the duration is simply duration of battery, simply 2000 by 60 hours, which is what? 100 by 3, approximately 33 hours. All right. Now just three more theoretical questions. Just as a refresher, a communication receiver performs the following tasks in which order? So, first task is synchronization, next, channel decoding, then channel estimation, then equalization. So, these are four of the tasks that a communication receiver performs, and the order would be first you have to synchronize. So one is first, then you'll do estimation, then you will equalize, and only then you will decode. So obviously, transmitter and receiver should be properly synchronized first before doing anything. Then you can use channel estimation to estimate what was the path loss, what was the time delay, all that. You'd use channel estimation for that. Nowadays, they use sophisticated machine learning algorithms to do it. They'll train on data sets and all. So you can use SP and ML for that if you're interested in doing uh, something related to machine learning. You can look at channel estimation. Of course, other parts also these days. almost everything they're trying to do using machine learning because the amount of traffic is too much. Then once you are done with estimation, equalization is done to remove intersymbol interference, which is mostly caused by uh, signal arriving in multiple paths. And then finally, once all this is done, you will do channel decoding, which is for error correction. Question 15. The major application areas or area of 5G is or are enhanced mobile broadband, ultra reliable low latency communication, massive machine type communications. D, all of the above. In the final lecture of the week, I think Professor talked about 5G, and the answer is all the above. But this is a course from 2017. That's why they're still talking about 5G. And now 5G is already here. Everyone should start thinking about 6G. So I suggest that by the end of the course, when you're giving feedback, you ask the NPTEL team to update the course so that they can make new lecture videos and add content. Maybe even if they don't revamp the entire course. But if a lot of students are demanding for something, they might add weeks, or they might offer a newer course from a different IIT whoever is working in 6G, 5G in recent times. If you have doubts regarding course content, it's better to ask in the Google group because I'm not a regular TA for this course. So I didn't design the course and I didn't set in the question papers. I was not involved with the creation of any of the content. So if you go to your uh, course page, there is at the top announcements about the course and Q&A. If you click on Q&A, you'll be It will say you are being redirected to Google discussion forum where you can discuss your queries with the course faculty. So Professor David will and his direct students will be interacting with you. And there you can click on continue, and then it will take you to a Gmail group. Because I am not exactly working in this field, so I might not be able to give you satisfactory answers. Okay, there is one final question, which is in a massive MIMO system, beamforming is a concept of channel estimation, B error control coding, C directional transmission and reception, D channel equalization. And beamforming is part of directional transmission and reception. So if you have a single antenna like this, you might have seen pictures of an antenna. When you radiate, you'll be radiating in a lot of different directions. It will be spread out, which means a lot of power is just wasted. So beamforming is a method to focus your radio waves in a particular direction as much as possible. And in MIMO, there will be multiple antennas arranged in an array usually, which will help you with this type of beamforming. And most of the stuff is done through signal processing now. So if you want to know the underlying theory behind the formation of beams and all, you can take a course on radiating systems. If you want to know how beamforming is actually done, you should try to take a signal processing related course or a communication system related course. Alright, that's it for today. Most of the questions are just basics from digital communication. I try not to give options wherever possible so that you don't heavily rely on the options. because a lot of the time you can just get the right answer by elimination if you are given options. It's better to understand the concept and solve it yourself. All right, I'll meet you guys next week with newer content. If you have any doubts, you can ask in the discussion forum, or you can ask me next week. All right, bye bye.